to everybody. So, today we will see how we can define the coordination number of any metal complex, which is a most general term related to some other species as well. In solid state also we can use this particular terminology, as well as in simple inorganic compound we use this particular number. So, in solid state what we find that if a particular center is attached to some more like this one, where the central bigger one is attaching to 4 such species in a typical tetrahedral geometry, then we can consider that this has a coordination number of 4. Similarly, the simple species like the corresponding inorganic anionic species such as permanganate anion, we all know that KMnO4 when dissolved in water we get MnO4 minus, and in that particular case that manganese center, which is in +7 oxidation state, is bound to 4 oxygen atoms, and again in a typical tetrahedral geometry. So, we get something where in 3-dimensional space how the entire species will behave and how the manganese center will activate some other atoms is also clearly visible if we consider the corresponding coordination number of this permanganate anion. Similarly, some inorganic compounds like boron trifluoride, by knowing the stoichiometry of the compound we can see that boron is attached to 3 fluorine atoms. So, initially only that particular information is sufficient to us to say a coordination number of 3 to boron, but afterwards if there are different possibilities related to this coordination number, we will find that in one particular geometry is favored compared to the other possibilities, where BF3 molecule will remain in that particular geometry. So, coordination number, the geometry, and sometimes the corresponding stereochemistry of the coordination compounds, they are all interrelated. So, if we just proceed in this manner for this first class, which is devoted to coordination number part 1, and how we can define this particular system is that the total number of points what are attached to the central element, what we are just now discussing, the total number of fluorine atoms attached to the boron center, we can call them as the coordination number. Similarly, the total number of oxygen atoms attached to the manganese center in permanganate anion is also known as the corresponding coordination number of manganese center in permanganate anion, and it can vary from a small number of 2, and sometime it can also been observed in recent time as a corresponding coordination number of 1, which is very unusual. If we have a huge and bulky ligand center and which can only allow one point of attachment, the number of points of attachment is important. If it allows only one point of attachment to the metal center, we can consider in that particular special case we can have only a coordination number of 1. Similarly, very smoothly we can go from a coordination number of 2 to 6. 6 will give us a corresponding octahedral geometry that we will find, and beyond that it can go to up to 16, where we can have some heavy metal centers like lanthanides and actinides, which has a size of say some compared to the 3D metal ions relatively bigger tennis ball like structure of size. So, it can attach more number of donor atoms and more number of points of attachment it can have, and it can have the corresponding coordination number up to 16. So, what we have just seen during the IUPAC nomenclature of some compounds, we have encountered with the corresponding medicinal coordination complex, which can be used as very good medicine, which is diamine dichloroplatinum. And this diamine dichloroplatinum immediately tells us the number of ligands giving the corresponding attachment to the platinum center. We have 2 amine ligands and 2 chloro ligands. So, we have these 2 chloro and 2 amine, and this particular molecule is in cis form. That means 2 of the chlorine atoms are in the 90-degree position, they are not 180-degree apart. So, is cis diamine dichloroplatinum, and as the definition tells us that the total number of points of attachment. So, this platinum center will have a total number of points of attachment equal to 4. So, the corresponding coordination number of this platinum center is 4. So, apart from its oxidation state, what we all know related to knowing the molecule, this is platinum attached to 2 neutral ligands and 2 anionic ligands, giving a corresponding oxidation state of platinum in +2. So, we get the corresponding oxidation state, and next the number of attachments to the center gives us the corresponding number as the coordination number, and sometimes we abbreviate it as Cn. So, the relative size of the metal ions and ligands are the corresponding determining factors, and the relative size of these ligands and metal ions will serve the purpose of choosing the corresponding coordination number. So, if we have a corresponding small metal ion, that means the metal ion sizes are important, and if we can have relatively bigger and bigger one. So, what we immediately consider it as, it can be the corresponding this manganese which is in +7 oxidation state. So, the smallest one is in +7, then we can have +4 or we can have the +2. And then the size of the corresponding ligands, the smaller, the medium size ligand and the bigger ligands, say the corresponding typical anions, what we can see as the corresponding salts, F minus, then Cl minus and then I minus. So, this particular one will, how many of these size parity can take place around a corresponding oxidation state of the metal ion as +2, +4 or +6, that will basically dictate us what will be the resultant coordination number of this particular combination. So, the relative sizes which are dictated by different electronic factors such as the charge, that means what is the corresponding charge on the metal ion and the corresponding charge on the ligands. If the ligands are negatively charged, they are not neutral ligands. So, this particular charge is also dependent on the electronic configuration of the metal ion. We all know the number of electrons what are occupying the different d levels in case of 3D elements, whether the electrons are in the dx square minus y square or dxy orbitals, that will provide us different sizes of the metal ions, and we get the corresponding high spin and low spin configurations. The sizes of these high spin and low spin configurations of the metal ions are different. That is why we get in our system, in our body, in the blood, the corresponding size of the metal ions iron in myoglobin and hemoglobin are different, and when we pass from one particular configuration to the other, and in one case it is sitting above the porphyrin ring and in another case it is fitting nicely within the pocket of the porphyrin ring, and that gives us a very important phenomenon in blood which is known as cooperativity. So, these size factors are definitely a tremendous role not only in coordination number for the different metal ions in metal complexes, but also in biological systems which are dealing with some metal ions. So, these competing effects are described by the term ionic potential. If we consider the charge and the radius and the corresponding ratio of these two, we will be talking in terms of the corresponding ionic potential. So, ionic potential of the metal ion will control the corresponding coordination number for the different metal complexes. So, we get like that of our solid state geometry, the radius ratio. The bigger the charge on the central ion, the more attraction there will be for negatively charged ligands. So, if we have the negatively charged ligands like fluoride, like chloride and iodide, the more attraction there will be if the charge on the central ion is more. That means, if we have a +7 charge on the metal ion, the corresponding attraction between this charge and this negative charge will be more. But when we have the charge, the smaller the ion becomes. That means, when you have the +7 oxidation state for manganese, it will have a smallest size in the series, which then limits the number of groups able to coordinate. So, when the size is small, we cannot accommodate or we cannot cover the corresponding metal ion by large number of ligands, though the corresponding attractive force between the positive center to the negative center is more. So, we have several situations like that of our thing where we have a coordination number of 2. So, how we get very simply the coordination number of 2, which is the smallest one where we can have a corresponding coordination number of 2, and this is also giving us some practical example for identification of chloride or the silver ion. So, when we have unknown chloride in the system in any form, we add silver nitrate, the water solution or aqueous solution of silver nitrate as the reagent, and we get silver chloride as the precipitate in the medium. So, one silver chloride is getting precipitated, which is white in color. So, we have to identify that this particular precipitation is due to silver chloride. So, what we do, we just simply add aqueous ammonia solution, and when we add aqueous ammonia solution, we should at the same time consider that we are just looking for something where silver ion is the metal ion center and what we are adding as reagent, aqueous ammonia is our reagent and which can be a good ligand. So, what we get, we can have the corresponding interaction between silver chloride and the amine complex resulting in corresponding silver amine coordination complex, which is soluble. So, we have the precipitate which is solubilizing due to the addition of the ligand as ammonia. So, what will be the structure? That is very important. So, first of all, if we just exactly or precisely know the formula that silver has only the ammonia in its environment because it is soluble and we have plenty of water molecules around, and we should also establish at this particular point that water molecules are not interacting with the silver centers in the ammonia molecule. And this particular one will show that this is the corresponding structure what we can have for silver and 2 ammonia molecules with a cationic charge on the overall complex. So, basically we get a corresponding 2 points of attachment to the metal center by 2 ligands. As a result, we get a corresponding coordination number of 2. So, this is the well known example for silver 1 and it has a low charge and an ion at the right hand side of the D block indicates smaller size. So, silver, copper 1, silver 1, gold 1 as well as zinc, cadmium and mercury also. So, the right hand side D block elements can provide us only some low coordination number because the charge is less. So, when we talk about the corresponding compound as silver 1 or the gold 1 or the mercury 1, we can have only corresponding coordination number of 2. And this particular case, when we get that silver chloride is reacting with ammonia giving AgNH3 whole 2 plus, what we have seen just now that the corresponding reaction is like this. Similarly, if we change the corresponding ligand from ammonia to cyanide and we get another species where the ligand is the anionic one. So, what will be the corresponding structure if we have cyanide as the corresponding silver or cyanide on gold. So, cyanometalates, these are all a general group of molecules which are known as cyanometalates, and these cyanometalates providing us some complexes where Cn minus is the ligand and Cn minus is a very good nucleophile and is a very strong ligand. So, it is a strong one and is a good nucleophile also. So, similar to the binding of ammonia, it can also bind from 2 points. That means, if we have M, we can have L this side, and L we can have L from these two sides. So, whenever we are talking about this coordination from this ammonia or cyanide, we can have some important informations at the same time, that if we have the corresponding ligand instead of ammonia, some ammonia like ligand, and the organic molecule like this bidentate chelating ligand ethylene diamine. So, how ethylene diamine can react with silver 1 or gold 1? So, in this particular case, if we have this silver one side, and if we try to have this NH2 function from this end and NH2 function from this end, we will see that whether it can span this entire range, that means whether it can span an angle of 180 degree, which is not permissible for a corresponding bite backbone as ethylene. So, what we will find that we have only the monodentate coordination of ethylene diamine from one side and another from the other side, giving rise to a different type of species, but only the monodentate ligation is permissible to the silver center, or if it is with the gold one, it will also give the corresponding interaction from one point of attachment only. So, this gives us some important reaction also due to the formation of this AuCN2 minus, which can also true for other charged monodentate ligands like chloride, like bromides, and this particular one, the elemental gold, since the cyanide is a very strong ligand, the elemental gold in the metallic form can react with cyanide in presence of oxygen, and it can oxidize the gold center to the corresponding gold 3. And this particular one, where the gold is present in the +3 oxidation state and AuCN2 minus is forming along with the formation of some 8 hydroxide molecules. So, medium turns to be basic from the 4 water molecules present over there along with one molecule of dioxygen. Since it is a very strong and powerful ligand, so cyanometalates are generally prepared. How we can prepare all these cyanometalates is that they are generally prepared by direct reaction of cyanide salts with simple metal salts. So, if we use the corresponding potassium cyanide or sodium cyanide, we can use it directly with the simple metal salt, or sometime we can use with the corresponding metal in the elemental form. So, elemental form is reacting with this cyanide giving this, and for the purification, if H plus is present, no other corresponding cationic species is present like potassium or sodium, we get this as the corresponding hydrogen form HAuCN2. And this particular procedure, that means this corresponding complexation procedure, is useful for the purification of the gold, where the gold quality is not good. Some impure gold can be treated with this and it can be leached out as the salt, and followed by reduction again back to the elemental gold can give rise the pure variety of gold in our hand. Now, we just simply move on to a corresponding coordination number of 3. So, in this particular case, which is not very common for first row transition metal ions, examples with 3 different geometries have been identified. So, how we can get those 3? So, which is simply the trigonal one, where the metal center is sitting at the center and 3 oxygen or 3 fluorine or 3 chlorine atoms are attaching at the 3 corners of a regular triangle. So, if you have a regular triangle and it can bind to these 3 points with this oxygen add fluorine, we can get a corresponding coordination number of 3. It can have a pyramidal structure at the same time. So, this is trigonal planar, this is pyramidal, and this is T-shaped. The third variety is basically the corresponding one is as the T-shaped structure. So, these 3 different configurations are pretty common. So, the first one, this one, which is basically the planar one, where this particular center it can be occupied by the metal and is attaching to 3 ligands. So, if we have the metal at the center and 3 ligands at 3 positions, 3 different positions of the equilateral triangle, we get this particular geometry, which is known as possible for boron trifluoride. So, boron is there, which is attaching to 3 fluorine atoms, giving rise to boron trifluoride, and we all know what the corresponding structure, because this particular can react with another fluoride anion to giving rise to a different species, which is a well known anionic species or corresponding species, which is present with so many metal complexes as tetrafluoroborate anion. So, this tetrafluoroborate anion have a different geometry and its coordination number is also changing. So, if we have a coordination number of 3 on the left, we can have a coordination number of 4 on the right. So, this is therefore a planar geometry and this is a tetrahedral one. Similarly, if we can have this particular center is occupied by the metal, we can have 3 ligands at 3 different positions. Similarly, you can have the corresponding pyramidal geometry. So, this particular central metal ion or the other atom, if it is moved upward, we can have the corresponding geometry like this. That means, this is sitting above the corresponding trigonal plane formed by 3 white spheres. So, we can have the corresponding species like this, and if we have this particular geometry, which we will call it as pyramidal. So, this pyramidal geometry or some distorted equilateral triangle. So, sometime we get a typical pyramidal geometry or distorted equilateral triangle. And these are also possible to have with silver triiodide as Agi3 minus. So, which gives us a corresponding distorted equilateral triangle geometry, or sometimes some particular case this is moving from the planar structure which we can have with the 3 ligands. If these 3 ligands are in plane and if the corresponding metal center is sitting above, we get a corresponding pyramidal geometry. And the third one, the third variety, which is pretty important to know, which is basically a T-shaped geometry, where these two atoms which are 180 degree apart, giving rise to a angle of 180 degree from one side to the other, but the third one is in between, which is giving 90 degree to each other. So, in this particular case, if we have a planar geometry, we will be getting an angle of 120 degree around the metal center. If this is a pyramidal structure, we get around 105 degree, but when this is T-shaped, we get two types of bond angles. So, metal ligand bond are different. So, this particular M L and this M L will have an angle of 90 degree. This L M L angle is also 90 degree, but this L M L angle is 180 degree. So, this T-shaped structure, which is not very common, so all the different types of T-shaped molecules like that of this pyramidal one, because one more example for this pyramidal structure is ClO3 minus, the chlorate anion. So, when we move from the chlorate to perchlorate, we get a corresponding structural change as well as the coordination number change. Here, like this BF3 to BF4 change, here also we get a corresponding coordination number of 3 to a coordination number of 4. But in this particular, it was a change from pyramidal to a tetrahedral structure. Here we have a, instead of planar structure, we have pyramidal to a tetrahedral geometry. So, the best example for inorganic molecule having a T-shaped structure is ClF3. So, this ClF3 gives us some immediate idea that some metal complexes can also have this type of geometry. So, this geometry is not very uncommon, with an angle of 180 degree on this side and another as an angle of 90 degree on the other side. So, how we get this from a typical coordination compound? So, if we have a typical organic ligand, like this, which is known as the corresponding triazine. So, the reaction of this triazine ligand, obviously it will have one hydrogen over here. So, this reaction of this triazine with copper 1 salt, how it goes? So, this gives a very useful molecule, is a binuclear compound. So, what we get? We get a copper 2 compound or copper 2 complex, where this nitrogen will bind to one copper and this will bind to another copper. And through this deprotonation of this hydrogen, we have a negative charge on this. So, on the other hand, that means the other side of the compound, we can have the same thing with one negative charge. Since both the two copper centers, we utilize this as a very well known starting material of copper 1 with coordination of 4 emission molecules over it, and which can be a salt of PF6 or perchlorate. So, it can be a salt of PF6 and perchlorate. And now, if we have some copper-copper bond or copper-copper interaction, we get a corresponding coordination number of copper centers 3, and which is also T-shaped. So, this is a very unique example where we do not have any other option for any other type of geometry. Only if we have a copper complex, we get this particular geometry, and this type of binding is very common in copper chemistry, and this triazine type of binding is also possible if we have the simple acetate group, and acetate group also binds like this. So, the binding of these two are of similar type. So, we have similar type of binding which we are following with triazine and which we are also following with acetate anion. But since two such triazine molecules are rightly attaching to the copper center, we have a typical center for this copper-copper interaction, and which is basically a T-shape from both sides. So, this gives us a very useful example of the center where we can have this particular geometry which is T-shaped with a coordination number of 3. So, all these examples we can have from this useful book of Messler and Tar. Then we just move on to a typical coordination number which is very much available to us, is corresponding coordination number of 4. So, once we have a corresponding coordination number of 4, we have in our mind the corresponding compound is the simple one which we are studying from our school days, is the methane molecule. So, if it is methane molecule, it will have a corresponding coordination number of 4. Similarly, if we have the example of MnO4 minus, just now we have seen, then tetrafluoroborate anion, then perchlorate anion. So, all these are the typical examples of coordination number of 4 in a typical environment which is a tetrahedral environment. But how quickly we get a typical example of a coordination number of 4 where we have the metal center and we have 4 ligands. So, it is a difficult choice for us when you react a typical metal ion with 4 such ligands. such as if we want to make the corresponding FeCl4 minus. So, how we can make this molecule and what are the number of attachments if they are all only the Cl minus attachment or some more water attachment, and what are the geometry of these 4 chloride anions around the iron center, that will tell us the corresponding geometry of the product which we are talking as the corresponding ferrate anion. So, tetrachloroferrate anion, what will be its structure. So, this particular geometry which is tetrahedral in nature is therefore a most common one, but the other variety also we can encounter is the corresponding square planar geometry, and they are found almost exclusively with metal ions having a D8 electronic configurations. So, if we have a D8 electronic configuration, we think that we can have the corresponding geometry as the square planar one. So, we find that the other alternative for it is the tetrahedral geometry, and in case of cobalt we can have a large number of tetrahedral cobalt 2 complexes. And the well known example, we know that the corresponding tetracarbonyl nickel. So, the tetracarbonyl nickel which is tetrahedral in structure, and also we can have the corresponding cobalt, this FeCl4 minus also we have seen similarly cobalt CoCl4 is also tetrahedral in nature, then cobalt tetrathiazine to anion is also tetrahedral in structure. So, these are the very good useful examples where we see that the cobalt center is preferring a tetrahedral geometry, not favoring the corresponding octahedral one. So, these are therefore the very useful examples of coordination number of 4. Then another example of the corresponding compound is tetrakis triphenyl phosphine palladium. So, like surrounding the nickel center by 4 carbon monoxide molecule, we get the tetrasan carbonyl nickel center. Similarly, one bulky phosphine ligand we are introducing here. So, like ammonia, we have the lone pair of electrons, and those lone pair of electrons are useful to bind the metal centers, and we can have so many types of metal complexes like hexaamine, tetraamine and the pentaamine complexes. Similarly, if we just use the phosphine center with 3 bulky phenyl rings. So, these are bulky phenyl rings. So, it is a very bulky ligand, and this bulky ligand is therefore very much useful when it is binding to the metal center, and this we can know this binding, that means the corresponding metal amine complex and the corresponding metal phosphine complex. So, the volume of this, that means the volume of this ammonia molecule this volume is small. So, this particular ligand volume will not control the corresponding geometry around the metal center, but when we have this phosphine binding and we see that this particular one, we have a funnel type of structure, and this funnel type of structure can give rise to some cone angle which is known as Tolman's cone angle, and in case of triphenyl phosphine it will be around 145 degree. So, these substitutions on the phosphorus atom is very important to change the corresponding cone angle. So, this triphenyl phosphine, it can have some other triphenyl phosphine, substituted triphenyl phosphine, that means we can have PR3 molecules, and depending on the nature of this R, we can change the corresponding cone angle. In some case it is less than this value, or in other case it is bigger than this value. So, the changing this particular cone angle, we basically have, we are just basically blocking, we are responsible to block this particular side. That means, this particular one can give rise to some amount of steric crowding. That means, this particular part, this particular size is not available for binding to some other ligand or some other donor atom, which was not possible in case of ammonia. So, ammonia can not have that much choice, and we can have, as a result, we can accommodate 6 ammonia molecules around cobaltic ion, that means trivalent cobalt, which is not possible. That means, we cannot have a cobalt PPH3 whole 6 molecule in our hand, similar to that particular ammonia, because the steric crowding would be more, and we will not end up with any situation where 6 phosphine ligands can go and cover this particular cobalt center systematically for an octahedral geometry. So, if we just go down for other metal center, you can go from cobalt to rhodium to iridium. That means, you can move from 3D to 4D to 5D metal center. That means, we want to increase the size of the metal centers like this to this to this. So, we can have 3D, we can have 4D, or we can have 5D. So, as we move to 5D also, so when we move to 5D, we have the bigger size of the metal center, but it is not possible to accommodate this number of phosphine ligands surrounding these metal ions. So, it is not always very much useful or very much preferable to have or move from one metal center to another to accommodate the bulky ligands. So, one such example is for palladium. So, when we attach this particular phosphine ligands and the corresponding oxidation state also we can have, that means, if we have the oxidation state in +2, +4 or 0. So, these are the 3 most possible arrangements for palladium, but if we go for palladium 0 oxidation state, the size of the palladium would be higher compared to palladium 2 plus, and we expect that we can accommodate 4 such triphenyl groups surrounding this palladium in a geometry which is very much similar to the formation of tetracarbonyl nickel center. That means, a typical tetrahedral geometry, and is a bright yellow compound what we can make with this compound, and which is definitely a corresponding geometry is like this, that means a tetrahedral geometry. These are the 4 phosphorus atoms surrounding this palladium center. So, we can have the one triphenyl unit, the second triphenyl unit and the third triphenyl unit, and on the back side you have the fourth triphenyl unit. So, we will have 4 into 3, that means 12 benzene rings are there surrounding this particular palladium center. That means, it is sterically highly crowded arrangement, but still we can get the corresponding stability of this particular palladium triphenyl phosphine compound, and we are not getting that this particular bond is labile, that means the palladium phosphine bond is labile and it is going away. So, like stabilization of this tetracarbonyl nickel salt, we also can stabilize the corresponding palladium center in 0 oxidation state as its corresponding tetrakis triphenyl phosphine derivative. So, what we get compared to this, also another geometry in the coordination number 4 is the square planar one, and this square planar geometry is also fairly rare and is included only because some extremely important molecule exists with this shape. That means, whenever we have the cyanide as the ligand, we get, that means we have NiCN whole 4 2 minus, and we get 4 cyanide groups attaching to the nickel center, and that will provide us a corresponding square planar geometry. Similarly, we can have the corresponding NiCl2 phosphine, which is used by Walter Reppe for the synthesis of acrylate esters from alkyne, carbon monoxide and alcohol. This is a typical example of the organic transformation, particularly the acrylate based esters for the formation of polymers afterwards, but the starting materials are very simple, which are acetylene type of molecules, that means alkynes, carbon monoxide and alcohol. And this particular compound, that means a compound with a coordination number of 4, NiBr2 phosphine 2, which is used as a good catalyst, and this particular nickel is in +2 oxidation state. But what should be the corresponding geometry of this compound when we attach simple phosphine ligands to the nickel bromide salt? The nickel bromide salt is well known to us, and if we attach 2 more phosphine ligands to it, we get a corresponding complex of nickel where the coordination number is 4. So, either we can have a square planar geometry or a tetrahedral geometry like this one, because this cannot remain in the square planar geometry. So, it will be distorted to a tetrahedral geometry. So, in square planar geometry we have the metal center and 4 groups attaching at 4 positions in a square plane. So, if it is tetracyanonickelate compared to tetracarbonyl nickel, it is square planar and all the nickel carbon bonds attaching to the nickel CN groups are in a particular plane. So, like this NiBr2 phosphine, this NiCl2 phosphine 2 is also tetrahedral in structure, and this spin triplet state we will just discuss afterwards, that how we get the corresponding spin triplet arrangement, which is related to the geometry. So, if we have some arrangement of Nix2Y2, we can have a tetrahedral geometry or we can have a square planar geometry. So, this tetrahedral and square planar geometry we can have when we study in detail the corresponding electronic configurations. We will find in all these cases the number of unpaired electrons would be different. So, we can have S is equal to some value for here, S is equal to some other value. So, in case of tetrahedral geometry we have 2 unpaired electrons, but here all the electrons are paired. So, if it is nickel in +2 oxidation state, which is a 3d8 configuration. So, all the electrons are paired. So, here you have electronic configuration S is equal to 1 and here S is equal to 0. So, this we will call as a singlet spin state, and this we will call as a triplet spin state. So, in terms of this singlet and triplet definition, wherever we get a corresponding compound which is of 3d8 electronic configuration, which is tetrahedral, that means we have 2 unpaired electron, it is giving rise to the corresponding spin triplet structure of nickel 2, but when we get the corresponding palladium 2 compound having the same number of chloride atom ligands and the phosphine ligand, we get a square planar geometry, that means a corresponding geometry is spin singlet. So, these are the basically clues. If we are able to measure experimentally the state, that means whether the complex is in spin triplet form or in the spin singlet form, we can infer immediately the corresponding coordination number as well as the corresponding geometry for these molecules. That means whether it is a nickel compound of coordination number 4 or a palladium compound of coordination number 4. Okay, thank you very much.